processes. I come back to this later. So this can be very important for ceramics industry, and here this ceramic BSCF membrane can play a big role. Here another application of our ceramic membranes is shown. You see here a cross-sectional. This is an oxide-based membrane, which is used in a big program together with Shell company to treat the wastewater coming from oil sand refinery. Also fracking technology. Here big amounts of polluted water are generated, and by means of our membranes you can purify or treat these waters to come up with portable water again, which is of course an important issue. So this is an example for the cleaning of harsh environmental polluted water. What we also do is we do some fine cleaning, fine filtration of polluted water. Here it comes down to parts per billion pollutions, also only trace elements. For this, we don't use ceramic membranes. In this case, we use an electrochemical process along with ultrasonic treatment using piezo ceramics. And by this process, we are able to get rid of pollutants coming from drug industry. So we can clean remains of antibiotics, also remains coming from agriculture. For example, glyphosate is here a big subject. So the treatment of water, rough treatment, but also the fine treatment of potable water is a big issue in our institute. And this is a summary of what we are doing in the field of this membrane and water treatment with our ceramic membranes. So we produce all kinds of nanofiltration units for industrial wastewater treatment. I was briefly talking about this oxygen generator for oxy-fuel processing. We do risk assessment and filtration of microplastic polluted water. We do some work in the field of power from waste and biogas, and also photocatalytic water treatment and water splitting is a subject in the institute. I have no time to mention all of this. If you are interested, feel free to send me an email, and I can send you further information about this. I now will switch to the next subject, which is storage technology in fuel cells. And I will start with storage technology. And here we do a lot of work in the field of lithium-ion battery along the whole value chain. You see here the value chain or the production scheme of lithium-ion batteries. Of course, this is a classical ceramic technology. You start with some ceramic powders, lithium cobalt oxide, iron phosphates, manganese oxides. And out of these ceramic powders, you make a slurry, which then is used to deposit or to make thin layers on such roll-to-roll processes. And from this, you can then manufacture different kinds of batteries. Here, a pouch cell is shown. You also can make round cells or prismatic cells, whatever you need. And here we cover the whole value chain. And we even started quite some work in the field of recycling, which is very important to recycle the lithium used here to make it really environmental friendly. Why is this a subject for ceramics people and not only for chemists? This is briefly illustrated on this slide here. You see here, it's very important to customize the morphology of your battery powder. Here, lithium cobalt oxide is shown. And you see very advantageous for battery applications is this spherical morphology. And it's good to have big spheres and smaller spheres because this gives high packing densities. You get a lot of this material in a certain volume. And of course, this is good for the performance of a battery because then a lot of charge can be stored in such a battery. But here on different scales, it's shown that this is not sufficient only to make this spherical morphology. When you zoom into such a sphere, you see here that each of these particles has again to show a certain kind of morphology, a porous structure in order to allow the electrolyte penetrating into the whole volume. And the whole thing is optimized down to the atomic scale in order to improve the performance of a battery, safety-wise, power density-wise, energy-wise. here a lot of optimizations can be done applying ceramic know-how. That's what we are doing. And we are very proud that recently, last year, we were able to start a big alliance with CATL. This is the second largest company in the world manufacturing lithium-ion batteries. And we have a joint R&D center now here in Germany where we jointly develop new kinds of battery production technologies. And very important here is to note that we not only cover here the process technology of the ceramic materials, we try to combine this with new kinds of sensors, actuators in the process technology, machine learning technologies, artificial intelligence, in order to improve the yield in the production. And it's important to note that right now in conventional production, there's still a pretty low yield in the battery manufacturing. And by developing such kind of machine learning technologies, you can improve the production yield and the costs by this significantly. So this is a big project. I also was mentioning that we do a lot of work in the field of recycling of these lithium-ion batteries. We also just founded a new recycling center along with a university close to Dresden. Unfortunately, I see this is a German slide, but what we are basically doing is we disassemble lithium-ion batteries, make a mechanical disassembly of this, and then by some processes, we are able to come up with a certain kind of material, which then can be separated from cobalt and nickel. And by CO2 processing, we are able to directly recycle lithium carbonate out of this, which then can be used for the battery directly. So this is a good process for lithium-ion battery recycling. You can use the same process, by the way, for treating raw materials, mineral raw materials to gain lithium carbonate out of these raw materials. And we have some of this also here in Germany. So much about lithium-ion technology, which right now is a very important subject in our institute for mobile applications, cars, electromobility, things of this nature. Of course, we are also working on energy transition things. So for the big picture, when you want to go away from hydrocarbon fuels purely to renewable energy, which are not base load capable, it's also important to have stationary storage capabilities. Here also, electrochemical batteries can play a role. In this case, we don't believe in lithium-ion batteries. Here, we look into another kind of technology, which is sodium nickel chloride technology. It's well known already for 20 years under the name of Zebra technology, but there are still quite some challenges. And here I give the electrochemical reaction equation. And you see the basic active material in this battery is sodium chloride. Sodium chloride is the same stuff that you put into your meals, and it's extremely available. So from a materials perspective, this is a very interesting kind of battery. And if you only look into the material costs, you can achieve costs below $30 per kilowatt hour. Of course, this is just a very rough estimation because you also have to consider production costs. And this is the key. So the core element of this battery is this ceramic beta aluminate. So this is a sodium conducting material. It's the electrolyte, and it's very hard to manufacture this. So this is right now the cost driver. And in our institute, we were able to develop a new production technology. So we now can make these electrolytes by a continuous extrusion process, and we combine this extrusion process with an injection molding process to directly make tubes with an end-capped tube here. And this decreases the production cost compared to conventional processes by more than an order of magnitude. And this makes this battery very cost efficient for stationary applications. Here you just see a view into our pilot lines where we now try to upscale this technology. The big advantage of sodium batteries compared to lithium-ion batteries is not only availability, it's also the process safety. So here a comparison for stationary application is shown. Here we see our sodium nickel chloride batteries compared to lithium batteries. When you use a lithium battery for stationary applications, you have to operate the battery in a very small temperature window. If you leave this window by plus minus 2 degrees, you will lose your warranty. And that means when you have such a system, you have to put a lot of know-how and a lot of effort in the active cooling or in the active temperature management of such a system. And this consumes a lot of energy and it has a lot of costs. And you don't need this with this battery. So this is the sodium battery is a high temperature battery. And the temperature is generated during the discharging of the battery by itself. So this battery doesn't care if you operate it in the desert or if you operate it in the Antarctica. So it always has constant temperature and it has a passive cooling mechanism. The other advantage is safety. So if you have a problem with a lithium-ion battery, you have a thermal runaway effect. So such a battery can catastrophically ignite, and this leads to a disaster. This does not happen for the sodium battery. If you have a problem with a cell, it simply will turn off and the system will continue to operate, so it's inherently safe. And this decreases the cost from a system level significantly. So for stationary applications, we think that this battery technology, also ceramic battery technology, has a lot of advantages, and we are, as I said, now upscaling this technology. I also would like to mention that we are not only working in conventional lithium-ion batteries and sodium nickel chloride batteries, we also do significant work in the field of solid-state battery. And this is a challenging issue, but quite some progress is being made. I want to explain what the issue behind this by mentioning the famous Tesla car here. Right now, in these Tesla cars, very conventional lithium-ion batteries are used. So you have these round cells, and you basically put 8,000 of these cells into a car. So that is a very simple technology. Simply use batteries and put them into the car, but it's not a smart technology, because by integrating these batteries in the cars, you lose a lot of space, you have to contact, you have a lot of safety issues, so it's not clever because you lose a lot of system efficiency. Although these cells are very good performing on a system level in the car, due to this cumbersome integration, you lose a lot of power density. So we pursue another approach, so-called bipolar battery approach. It's also known for a long time, but there are still some technological challenges that we try to overcome. And what we try to do is not to put 8,000 of these batteries. We simply want to make one battery by a stack technology. We simply print these layers or the cells on top of each other. And we want to come up with one battery which fits to the chassis of the car, and then having a much better integration performance right now. We have quite good results on these technologies. So we use cobalt-free batteries for this. But this bipolar battery still contains liquid electrolyte. The next step is to substitute this liquid electrolyte by a polymer electrolyte. And then the next step to substitute the polymer by a solid electrolyte, sulfide or oxide-based pure ceramic system. So this is what we are working on right now. And here safety and power density would significantly increase. As I said, there are still technological challenges to really realize this on a technological level, but we are confident that we are able to do this because we already did it for another technology. So this solid state approach, this stack approach, is already realized in fuel cell technology. When you look into a PEM fuel cell, so polymer electrolyte membrane fuel cell, it's nothing else than such a approach is realized. You have a stack technology, you have a polymer for the ion conductor, and these systems already work well. And also for the oxide systems, we have these solid oxide fuel cells where this also already is shown. So the message here is in fuel cell technology, this technology is already available, and fuel cell technology is ahead technology-wise compared to the solid-state batteries, and we want to apply this know-how to the battery, and this is what we are working on. Yeah, and that brings me to fuel cell technology. Lithium-ion batteries, sodium nickel chloride batteries, solid-state batteries are all secondary batteries. That means they can be charged and discharged. A fuel cell is nothing else than also a battery, but a tertiary battery. That means you continuously distribute your active material to this fuel cell, and it never discharges, so it can be continuously used. So this is the difference between a fuel cell and a secondary battery. It's all electrochemical systems. And here you see the SOFC value chain. The core element is a zirconia, it's the yttria doped zirconia, which is then oxygen conducting. So this is the electrolyte material. By tape casting, you make such a membrane electrode assembly out of this. You see a 10 by 10 centimeter sheet. And by screen printing, on one side, you deposit nickel oxide, on the other side, lanthanum strontium manganate. It's a tenth of a millimeter thin, and this component then gives you 30 watts of electrical power if you have oxygen on one side and hydrogen on the other side. And the beauty about this fuel cell is it even works without hydrogen. You also can use conventional hydrocarbon fuels, such as natural gas, that you can use as long as the hydrogen infrastructure is not available. Out of these MEAs, you then make a stack. For example, when you stack 30 of these elements, you come up with such a stack of 1 kilowatt. 1 kilowatt, by the way, is sufficient to make electrical power for a single family home here in Germany. So the average usage of power is roughly 5,000 kilowatt hours per year. 1 kilowatt a year has more than 8,000 hours. That means you make more power by this element than you need for a single family home. The volume of such a stack is roughly 1 liter. And this is exactly what we did for certain kinds of applications. So for example, we developed for a heating company in Germany called Weiland a heating system which is operated on natural gas, and we implemented such a fuel cell, and then you can use the same natural gas not only for heating but also for making your power. We, by the way, did the same also for an Indian company called Empower or H2E, and first system demonstrators are being used in India right now as well. This is again a complicated chart showing our whole history in the field of fuel cells. We actually started already in the 90s, and in 96 we took over the IP from Siemens in this field because they discontinued their planar technology. They were focusing on tubular design, and based on this Siemens technology, we developed these stack components, which then were commercialized in several spin-offs that you see here. Empower, by the way, is an Indian company which has a German branch, and also some of these fuel cell stacks are being now developed in India. Based on these stacks, we developed several kinds of systems. I already mentioned this Weiland heating system, which allows to make micro CHP, combined heat and power applications, to produce from your natural gas not only your heat but also your power. Several other applications are shown here. I have no time to go into the details. Maybe a current project. So right now we combine such a fuel cell stack with a microturbine to even improve or increase the system efficiency. So with a fuel cell, you have an electrical efficiency in the order of 60%. If you combine this with a microturbine, you can go up to 80% efficiencies, or maybe even beyond. You see here, the fuel cells are stacked in the periphery of a turbine, in the turbine housing, so to say, to combine both systems in one unit. This brings me to another subject which is right now even more important. So I was talking so far about SOFC, solid oxide fuel cell. You simply can exchange the F by an E, and then you have solid oxide electrolysis cells. It's basically the same stack, yeah, operated in the reverse mode. So usually a fuel cell is operated, you have you make power, so you have hydrogen and you have air, and then you make electrical power. But the reverse also works. So if you have power and if you have water, then you can generate hydrogen with such a fuel cell system, electrolysis. And the beauty about this SOEC technology is it can not only convert water into hydrogen, it also can electrolyze CO2 into CO. So you also can electrolyze, so to say, CO2 from air into CO. And you can do this together, and this is then called co-electrolysis. So basically, you can actively remove CO2 from the air and then in one step produce this syngas, H2CO. This syngas then can be used to make all kinds of e-fuels or higher added value products, which I will mention later, for example, by Fischer-Tropsch technologies that we also implement. So it's a very nice technology for hydrogen economy and also for CO2 reduction. This is summarized here again. And one big advantage that I did not mention yet is, or maybe I go back one further, it also uses heat in the energy balance to produce this synthetic gas. So you see here, the higher the temperature of your system, the lower the electrical power demand. And if you go to 830 degrees Celsius for operating, you can use roughly 3 kilowatt hour electrical power to make 1 norm cubic meter of this synthetic gas. This synthetic gas has more energy content than the 3.1 kilowatt hours shown here. That means the heat directly goes into the energy balance. And that means in all cases, when you have waste heat, this is a very nice and very efficient process. Here we see the performance of our SOEC cells, also these MERs, in a long-term test here. You see we have a very low degradation. You can even not see it on this slide for longer periods. So we have proven more than 40,000 hours of performance, and degradation rates are below 0.6% per 1,000 hours, which is an excellent performance. And when you use these cells into a stack, here you see the stack performance. You see also that you can use this. Here's again a long-term test is shown 5,000 hours. The operation was switched from pure water electrolysis to co-electrolysis here, which is easily doable. Again, you see almost no degradation in these stacks, so it's working very well. Here a 1 kilowatt stack is shown. Here you see our 20 kilowatt stacks by modularizing these stacks. So very important technology. And we then combined this technology to a very complex system, and we are very proud on this. Here you see the worldwide first fully integrated SOEC co-electrolysis Fischer-Tropsch system. So in this unit, all of these processes are combined. So basically, water, steam, CO2 comes in, and electrical power, then this co-electrolysis is done. And the syngas, which comes out of this, is used for Fischer-Tropsch evaluation. And then as products, you can get all kinds of products such as higher alcohols, waxes, e-fuels, whatever you need. You can simply open a valve and then get these materials. The CO2, by the way, for separation of CO2 out of air, you need, again, ceramic membranes. We developed carbon-based membranes for these applications to separate the CO2 out of air to be able to use this then in this co-electrolysis unit. Here you see some details about our Fischer-Tropsch technology. We are here developing all kinds of catalysts iron-based, also cobalt-based catalysts that then can be used in these integrated systems. And here you see some of the products. Also out of this synthesis gas made by Fischer-Tropsch, you can make these higher alcohols, diesel, jet fuel, waxes. Also, you can make methane, methanol. For this, you even don't need Fischer-Tropsch. So this is a very capable technology for future hydrogen economy. So what I was explaining so far was this technology here, CCU, carbon capture and utilization. And as I was mentioning, here we have this integrated system available. Here we see the valve that you can open to get the different fractions of the products that you need. There's another technology we are working on, which is called carbon direct avoidance. This is, for example, important for steel industry. Here you use hydrogen made by this electrolysis to substitute the coal used in the process. And by this, you can produce green steel with a CO2 footprint, which has a more than 90% less CO2 consumption than in conventional steel production. Although here, big projects are being run right now in Europe and in Germany to test this. Yeah, everybody's talking about hydrogen economy. We as well. If you really want to make it environmental clean, you need green hydrogen. That means you have to make this hydrogen out of renewable power. And for this, you need electrolysis. So I was mentioning this SOEC, solid oxide electrolysis, that we are developing. We are also doing some work on polymer electrolyte membrane electrolysis and on classical alkaline electrolysis. Here also ceramics play a big role. I want to stress, to emphasize again the advantage of the SOEC technology. Roughly you need 3 kilowatt hours of electrical power to generate 1 norm cubic meter of this syngas. And this is much less power demand than for the other technologies when you have waste heat. And in a lot of industrial processes, waste heat is available also in ceramics industry, for example. And in the case that you can use the heat for your energy balance, this is a very advantageous process. If you don't have waste heat, then the other technologies are also very valuable. That means we have to develop all 3 of these technologies in order to generate enough green hydrogen. And what we are doing right now is we are trying to scale this up. That means from our kilowatt stacks, we right now to make bigger stacks, we have to go to gigawatt regimes in the case of electrolysis in order to produce enough hydrogen for a hydrogen economy. Yeah, and that brings me to my last slide. I hope I was able to show you that ceramics can contribute a lot to our issues in society, to get rid of CO2 and to increase energy efficiency. And this is what we want to try to bring together. In order to have a CO2-free environment, you need these closed cycle technologies. You need to close the energy cycles, the water cycles, the resources cycles. And here the components I was showing play a big role. You can look yourself into this picture. So that is what we try to do right now, combine all of these technology. And I thank you very much for your attention. Thank you very much. Thank you very much. Yeah. And best regards from Germany. So it's cold here. I hope it's not as cold in India right now. Yeah. So here we have 0 degrees Celsius, yeah, and no sun. So next time I come to India again. Yeah. Thank you very much. Yeah.
don't do that.
No, otherwise I cannot enter.
Okay. Oh, you have to sign up.
So this marks the end of the inaugural session. We will now have a short tea break. Tea will be served on the lawn in front of the KD Sharma Hall. Also, please note that after the tea break, the annual general meeting of Indian Ceramic Society will be held virtually. So I request all the members to join the meeting on time right after the tea break. And for now, please join us for a cup of tea. Thank you. Okay, the meeting will be at 5:30. Okay.
5 p.m.
5.
Okay, the AGM of Indian Ceramic Society will start the AGM sharp at 5 p.m. and it will be on the virtual mode in MS Team platform. I am sure all the members have received their MS Team link. Thank you all.
আমি রেডি করে দিচ্ছি। আমি রেডি করে দিচ্ছি।